Hello, this short video, I'm going to review the governing equations for solid mechanics. And in particular, I'm going to talk about a linear versus nonlinear approaches and what that means. So I'm going to go through the governing equations and their different forms and distinguish between linear approaches, also known as small strain approaches or geometrically linear approaches, and nonlinear approaches or geometrically nonlinear approaches, also known as large strain approaches. So the governing equations for solids. So there are 5 governing equations of Continuum mechanics: conservation of linear momentum, conservation of angular momentum, conservation of mass, conservation of energy, and then the second law of thermodynamics, which is an inequality. Typically, if we're interested in the stress and deformation within a solid, we're going to start with the conservation of linear momentum. So that's this equation here. And there are cases where we may consider the other equations too. If it's a thermal stress problem, we will consider conservation of energy as well. Or there are special cases, for example, shells and beams, where the conservation of angular momentum may be used as well. Let's start with the conservation of linear momentum. So this is a generalization of Newton's second law. So F equals ma. However, we normally write it as ma equals F. So we have v for velocity. So d dt of velocity, the rate of change of velocity is acceleration. But rather than multiplied by mass, it's multiplied by density, because this partial differential equation is given in per unit volume. So imagine it's mass divided by volume, density. And the right hand side is the sum of the forces applied to our arc. So this equation can be applied to any part or any individual point within a part or a material. So this divergence of stress, anytime you see a divergence, is imagine a small piece of material and you're summing the flow in and out of that piece of material. In this case, it's the flow of stress, which is like the traction vector. So it's like summing up the integral of the traction on any individual piece of material. So it's like summing the surface forces on any piece of material. And rho g of gravity. So if you have like a body force like gravity, then that could also be added. So this partial or any partial differential equation can be written in differential form like this. And so that essentially is applied at a point. So that's a conservation at a point. So maybe that's hard to grasp. So if you imagine you have a piece of material and you've certain surface forces on it and you have some gravity on it, and maybe it's accelerating, then as you let that volume of material approach 0, and then in the limit of that, you get this differential form of the partial differential equation. So that's kind of like the sum of surface forces at a point. However, you can equivalently write this equation in integral form. So if we just integrate each term over the volume, so omega here I'm using to refer to the volume. I'm not using v just to avoid confusion with velocity. So integrate over the volume of some finite size part and integrate over the volume over here. And we can also integrate this divergence of stress over the volume, but we can, by Green's Gauss's theorem, we can also represent that as a surface integral. So this circle here means we're integrating over a surface which is closed in space, like a closed surface. Gamma here represents the surface. And so the Gauss theorem says if you have a volume integral with a divergence, you can change the surface integral where the divergence changes to the normal multiplying with the outward facing normal vector on the surface. So this integral form is just an equivalent way of specifying it to a finite size part. There's another equivalent form which is called a weak integral form. So if this is the strong integral form, it's where you multiply this differential form by a weighting function and then you integrate over volume. So that can be a starting point for finite element methods, and it's another equivalent way to specify it. Okay, so what simplifications can we make to this equation? Well, we could ignore body forces. So it could just be mass by acceleration per unit volume equals sum of surface forces. We can also ignore inertia. So this doesn't mean that we're ignoring anything changing in time. It's just we're assuming that the acceleration is small. So the acceleration doesn't affect the system. So if we're doing a mechanical test in the workshop, and the acceleration would be very small relative to the surface forces on our part. So even though it's moving, and maybe it's moving at constant velocity, so the acceleration is zero anyway. So we can ignore mass by acceleration. So this gives what's known as a quasi-static form. It's not a static form because it can just the velocity doesn't have to be zero. It's just saying that the inertia is small. So when would the inertia not be small? Well, for anything that's happening at a high rate, like a car crash or something, then the acceleration or the inertia is typically non-negligible. And then to talk about linearity and non-linearity, we can assume small strength. So what do we mean by that? So the linear geometry assumption versus the non-linear geometry approach. So what do I mean by that? So let's imagine we have a block and maybe it's fixed at the bottom and we apply a non-zero displacement to the top. So as we pull it, most materials with positive Poisson ratios will contract, or materials with positive Poisson ratios will contract. So the area and volume of the material will change in general. And similarly, if we were to do that to an actual discretized finite element mesh, you can see each individual volume of material or area is changing. And if we look at any edge, if you're looking at the normal of those edges, they will be changing as well. So conceptually, if we take this quasi-static approach, this ignoring inertia and body forces, then the divergence stress is zero. And so conceptually, what you can think of this as is you could sum the force around any element or around any set of elements, and that would have to be equal to zero. So if you're summing the force, that would be equal to the area vector and an inner product with the stress tensor. So area by stress gives you your force. So the stress, if we were assuming Hooke's law, would be a function of U, or displacement, but also the area, which is changing in time, in this case, is also a function of displacement. So if this is a function of displacement, this is a function of displacement. When you multiply these two together, you're going to end up with at least some nonlinear term, some term that has a U squared in it. So a nonlinear function of U. So if we assume the deformation is small, so imagine that in this case it's quite a large deformation, but imagine we've applied a very small displacement, so maybe like 1/1,000,000% of the length of this, then you wouldn't change in these area vectors will be very small also. So in that case, it would probably be fine to ignore the fact that the S area vectors are a function of the displacement field. You could just assume they're independent of the displacement field. So making that assumption that the areas and the volumes and the area vectors are independent of the displacement field, that's called a small strain approach, or it's called a linear geometry or linearized geometry approach. So it's making the problem linear in geometry because you're assuming the geometry is no longer a function of the displacement. So then S would no longer be a function of displacement, and only your stress will be a function of displacement, and that may end up with a linear equation. So a linear equation, when we discretize this by the finite element method, we'll get some stiffness matrix K, and U is the list of the unknown displacements at the nodes, and that's equal to any externally applied forces. And then in that case, K will not be a function of U. However, that's a simplifying assumption, that small strain approach. And that won't work if the deformation is truly large. It'll just give us wrong answers. So the most general approach is you don't make that simplifying assumption. You allow for the fact that S is a function of displacement. So then even if you're assuming that Hooke's law or some simple material model, then even in that case, it will still be a nonlinear problem. This K stiffness matrix, each of its terms will be a function of the area vector, and the area vector will be a function of the displacement of the nodes. So this becomes a nonlinear problem. And potentially the force vector on the right will be a function of the displacement of the nodes. So then you need a method like the Newton-Raphson method or some iterative method to solve this. You have to solve it multiple times to account for the K as a function of U. So that's called geometric nonlinearity. And so, or a large string versus small string approach. But you can also get nonlinearity, and by nonlinearity, I mean K is a function of displacement in two other ways. One, with certain types of material laws, and two, with certain types of boundary conditions. And to give some examples for material laws, if you have plasticity, then we'll introduce nonlinearity. Or for loading, if you have like cracks or contact boundary conditions, there also will introduce nonlinearity. So if the deformation strains and rotations are small, then it's typically okay to assume the geometry is not a function of displacement, and that's called a small strain approach or a small strain rotation approach. But if the deformation is not small, then this assumption is inappropriate. And how do you turn this on and off in Abacus? Well, when you make a step, there's an option called nlgeom, or nonlinear geometry. By default, it's turned off. So by default, it's assuming linear geometry. So it's making this simplifying assumption of that the deformations are not large. So if you were using the default approach and the deformations were large, the answers could be quite wrong. So if you want to enable it, you just, when you're making a step, you enable nlgeom, or if you've made the step already, just right click on it and go edit step, and then you can then go to nlgeom and just enable it. And so how can we check if it's okay to use the small string rotation assumption? Well, if you're unsure if geometric nonlinearity is needed, then perform the simulation twice. Do it with nlgeom off, so a linear geometry approach, and nlgeom on, so a nonlinear geometry approach. If the results are different, then yes, you need a geometrically nonlinear approach. Then you have to use it with it turned on. If they're not that different, then it's okay to use the nlgeom off. And why would you do that? Well, it'll be faster to run. So by making this simplifying assumption, it means it doesn't have to do iterations, so it'll be faster to run, and that's why it picks it as the default. Then with more experience, you'll start to realize what types of cases need it and what types of cases don't need it. So for example, if you're looking at soft tissues, like biological tissues, typically if you were doing tests on those, they deform quite a lot, so you need a nonlinear geometry approach in those cases. But if you're looking at things like metals and very stiff materials like steel or aluminium, for just design cases, nonlinear geometry is mostly not important. The only time it becomes important is if you're really looking at applying large deformations to metals. So for example, in metal forming operations, then you would need to use nonlinear geometry approaches. What other sources? Nonlinearity in solid mechanics. So I've already mentioned these. So for a linear mechanical law, like Hooke's law, you would just have stress as linear proportional strain, but you have nonlinear elastic that introduces nonlinearity, or if you have elastic, so you're increasing the stress, and at some point, permanent deformation starts to occur. So that introduces nonlinearity as well. Or viscoelasticity, or there's other types, like all hyperelastic material laws are nonlinear as well. And then for loading, well, imagine you're displacing a block. So the force will be 0, 0, 0 until it comes in contact, and then it'll increase. So the force is 0, 0, 0, then it comes in contact. So this, if you take that plot of force 0 and then it changes its slope, that's a nonlinear function of the displacement field. So that introduces some nonlinearity. So that's contact, but there's also cracks as well. If you're pulling this beam apart and then suddenly it cracks at some point, it's nonlinear. So just be aware of that, and it will make the models slower to converge and longer to solve, and maybe it'll have problems solving them. So it's always good if you can do an approximate linear approach first, just to get some answer before you see if it's necessary to add extra complexity. So in summary, there's three causes of nonlinearity in solid mechanics: geometric nonlinearity, material, and then loading. And typically in Abacus or finite element softwares, they use a method called the Newton-Raphson method to iteratively solve these systems. So when you're solving Ku equals F, you might use Gaussian elimination or something similar. So they'll do that in this approach. So that gives the answer to the first guess for you, but then you update K and F in some way and then solve it again. So the overall outer iteration procedure is called Newton-Raphson, and that decides about how much you should correct U by each iteration. That's that.